In this tutorial, we will be discussing the energetics of solution formation. When a solution is formed, first of all you must have the similar polarities. Like dissolves like. In order for the solution to be created, first thing you need to do is that the solutes have to break apart. So that means that the interactions between the solute particles must be broken. This requires energy to put into the system. Then the solvent must make room for the solute. So therefore some of those interactions, not all of them, but some of them do have to be broken as well to make room for the solute particles. That also requires energy. So that means these are both positive because energy must be added for it to take place. Then for the solution to be made, new interactions are created. So the intermolecular forces are then created, and this is the X factor. This is the question as to whether or not the solution will be formed. The enthalpy changes, or delta H, in the formation of most solutions involve differences in the attractive forces between the solute and solvent particles. There are three different types of interactions that are occurring. The solvent particles being attracted to one another, the solute particles being attracted to each other, and then the solute and solvent being attracted to one another. In order for the solvent and solute to mix, you must first overcome all the solute-solute interactions, the attractive forces, intermolecular forces. And some of the solvent-solvent interactions. Once again, the attractive forces are the intermolecular forces. This creates the delta H, or the enthalpy of the solute, and the enthalpy of the solvent. Both of these processes are endothermic. You have to add energy to make that happen. At least some of the energy to do this comes from making the new solute-solvent interactions. These are the attractions, or the intermolecular forces, between the solute and solvent itself. So if there's ion dipole forces, things along those lines, this is going to be exothermic. It's going to give off energy in this process. So if we're looking at this, first thing that needs to happen is the separating of the solute particles. That's going to take energy for it to happen. Then separating of the solvent particles to make room for the solute. That's going to take more energy. So we had the solvent separated and the solute separated. When we add them together, we're going to get that energy back. So that's making the solution. If this gives off more energy than it's needed, we have a net exothermic process. However, in the process, if you don't give enough back, you have a net endothermic process. So you have to put more energy in, and it feels cold when it's mixed together. Whereas the exothermic feels hot because it's giving off the energy, because you have excess energy there. So let's break this down again. The solute to the solvent is greater than the solute to one another and solvent to one another. This is going to form a solution, because that means this takes more energy than this. If the solute to solvent interactions is approximately the same as the solute to one another and solvent to one another, once again the solution is going to be formed. However, if the solute to solvent is less than the energy than these, then this is the questionable section. It may or may not have the solution formation. If the energy difference is small and entropy is greater, then the solution will form. So what is entropy? It is the measure of the system's disorder or dispersal of the particles throughout the system. Notice we have neon on one side and argon on the other. Once this barrier is removed, naturally these particles want to mix together. And that's entropy. It's the measure of how much it wants to be mixed up. Energy is the drive to disperse throughout the system. Its processes occur because they have less potential energy. The solution formation may or may not lower the potential energy of the system, the solute dissolving in the solvent. For example, the spontaneous mixing of gases under the standard conditions. The difference in attractive forces is negligible. So in other words, they're far enough apart that they don't realize each other are existing. They have mixing because the energy of the system is lowered, spread out through the release of entropy. This is similar in mixing of solutions, of liquid solutions. Here we have water on this side, and we have a solution of salt water on this side with a barrier between. Once that barrier is removed, it spontaneously mixes throughout, producing a solution of uniform concentration. So what is the heat of hydration? The enthalpy of hydration is the energy that change associated with the energy added to overcome the intermolecular forces, such as hydrogen bonding between the water molecules, which is the solvent. The energy released in forming attractions between the water molecules and the ions in the ion dipole attractions. The heat of hydration is the energy or the heat released when 1 mole of the gaseous ions dissolves in water. So the solvent and the mixture added together. So here's the solvent and here's the mixture. Those two things added together is the heat of hydration. The heat of the solute, the enthalpy of the solute, is the opposite of the lattice energy, which is the attractive forces, the intermolecular forces between the ions and the solids. Therefore, the delta H of solution is the difference between the heat of hydration and the lattice energy. The lattice energy is always exothermic. There's a relationship between the magnitude and the size of the heat of solution to the heat of hydration. When the heat of solution is large and endothermic, in other words, the delta H is positive for the solution, then the amount of energy to separate the ions is more than the energy released from hydrating the ions. The hydration energy is less than the lattice energy. When we look here, the delta H of the solute is an endothermic process. The lattice energy is endothermic. The solvent and mixture added together is the exothermic solution, exothermic process. So here we have solid KF. This energy is the delta H of the lattice energy, so we need to separate that. You have to add energy into it in order for that to happen. The heat of hydration is the mixing of these two things together, which is an exothermic reaction. This overall process is endothermic because it takes more energy to add to the separation of the KF than it does in the release of putting the two things together. When the delta H of the solution is large and exothermic, in other words it's negative, then the amount of the energy is cost to separate the ions is less than the energy released from hydrating the ions. So the hydration is greater than the lattice. The delta H of the solution is then going to be negative because the solute, the delta H of the lattice, is less than the hydration. So in this process, if this was a different chemical, the arrow would go on further and this would be the exothermic portion.